Hello, everyone. I'm Florina Muntenescu.
I'm Manuel Vivo.
And we're engineers in the developer relations team at Google.
Today, we want to do a deep dive into these main topics, cancellation and exceptions in coroutines. And hopefully, by the end of the session, you'll be able to fully understand what's going on under the hood so that you avoid unexpected results when working with coroutines. And why are these topics that important? We'll spend like a full talk just talking about them. The thing is that with cancellation, it's going to help you clean up those resources when they are no longer needed. So for example, imagine that the user moves away from the screen and there are some ongoing work happening. That work might no longer be relevant, so we should cancel that just to not waste CPU and memory in our devices. And not handling errors properly can ruin your user experience. We developers spend a lot of time focusing on polishing the happy path. But sometimes showing that informative message to the user when something goes wrong is as important as the happy path. Yeah, not talking about crashes in your application. That could be pretty bad. Not ideal. Anyway, we want to start by covering the basics so that we all are on the same page when we introduce to more complex topics. And the first concept we are going to use, obviously, is the coroutineScope. And this is your entry point to coroutines. You can create a coroutine, you can call suspend functions. And because of that, it's going to help you keeping track of the coroutines and the work that is going on the screen. And as we will see throughout the presentation, it's going to give you the ability to cancel that ongoing work that it started and will be notified when a failure happens. And just to show some coroutine 101 code, you will see here we can define a coroutineScope, and we can call launch within it. So scope.launch will create a new coroutine. And if you notice, there is a job that is returned by the launch call, and also there is a job in the coroutineScope. So what is a job? A job is the handle to that coroutine, is the handle to that ongoing work. And it's going to model the life cycle of the coroutine. You will be able to wait for it to finish, or you will be able also to cancel it. And if you noticed as well, the coroutineScope could create a coroutine. And other coroutines can create more coroutines. And this is going to create a task hierarchy in which coroutines are going to be executed in. And obviously, the root of that hierarchy is going to be the job installed in the coroutineScope. Just to visualize it a little bit, you can see how the parent coroutine can create other coroutines. And we're going to see more of these diagrams throughout the presentation.
So coroutines have a set of states, are going through a set of states through their life cycle. So by default, we don't have access to these states, but what we have is a set of properties that are related to these states. So by default, a coroutine is launched eagerly. So this means that by default, it will be in the active state with the isActive property true. But you can also launch a coroutine lazily by passing the coroutineStart.lazy flag. And then you can move to an active state if you call start or join on the coroutine. But then, while the coroutine is running, it's going to be in the active state, and once it's finished its job, it's going to be in the completing state. But Manu just told you that we're talking about a hierarchy. So this means that the coroutine will stay in the completing state until all of its children have finished. So this is why, for now, we're in the isActive is true. But once all of the children are finished, only then we get in the completed state, where isCompleted flag is true. But if something happens, either when we're in active or in completing state, either cancel is called or an exception is thrown, then we get into the canceling state. And while the cancellation process is happening, we'll stay there, and only afterwards we're getting to the canceled state. To define the behavior of a coroutine, use the coroutine context that contains a set of elements. So the coroutine dispatcher, which defines the threading, the job that defines the coroutine lifecycle, a coroutine exception handler, and a coroutine name. And all of these have defaults. So by default, we have dispatchers.default. By default, we don't have a parent job. We don't have a coroutine exception handler. And the name is just coroutine.
Sure. When you create a new coroutine, it is going to inherit the parent context. But because this parent context is going to highly influence how cancellation and exceptions work, we want to be very precise when defining it. And we can say that the parent context is the combinations of the defaults that we saw before, the inherited context, and the arguments that you pass to the coroutine builders. And as you see, you can combine and concatenate coroutine context where the resulting context will be the elements from the right-hand side of the equation will overwrite those elements from the left. And the coroutine context, the coroutine that creates itself, will have the parent context with a new job. This will be a new instance of a job that will uniquely represent that coroutine, that ongoing computation. We're going to see this in a little bit more detail here. So by default, if you don't specify any context, there is no parent context, your coroutine will come up with this parent context. It has the dispatcher.default and coroutine as name. It's good for debugging. But now let's say we create a new scope, and we pass in this coroutine context as a parameter. So we have a job, dispatchers.main, and a coroutine exception handler that we defined somewhere else. And those are going to become the parent context, the elements in the parent context for any coroutine that you create out of that scope, at least if you don't otherwise override them. So now let's say with that scope, we are going to call launch, and we are passing dispatchers.io as a parameter. That parameter is going to become part of the parent context. So we have dispatchers.io. So what is the actual coroutine context of the coroutine we just created? It's going to share most of the elements with the parent context. We'll have this coroutine context here, and then the job will be unique to this coroutine. So this is the job that your launch returns, and that will be part of the coroutine context. The reason why I'm leaving the parent context and the coroutine context on the screen here is because there is an important part in this diagram, which is the parent job. And this is the job that is part of the parent context, and in this case, comes from the scope that we defined before. So now we ended up with the introduction. I think we are all good on the same page, and we're going to see cancellation in more details.
So we know that it's important to don't do more work that we need. We want to make sure that we're not wasting memory and battery life. So this means that if a lifecycle scope, let's say, finishes, like a user press back, we want to make sure that our coroutines don't run longer than they should, longer than the objects they use them. So rather, when that lifecycle ends, they should automatically call cancel on our coroutine, and our coroutine to be finished. So usually what we have is something like this. We would have a coroutine scope with multiple jobs part of it. But we don't want to track every job individually and then cancel each job on the row. But rather, for this, we use scope.cancel. So when we do this, the scope automatically propagates the cancellation to all of the children. So all of the children are now canceled. So we can say that when we're canceling a scope, all of its children are also canceled. But we have some cases, in the architecture components, we have two scopes, the viewModel scope and the lifecycle scope. So both of these make sure that this good behavior of cancellation when the scope isn't happening is already implemented for you. So this means that you won't need to call cancel by yourselves. So I think in general, chances are when you're using a scope, you're not going to call cancel, because usually you're using a scope that's provided to you, like the viewModel scope or lifecycle scope or some other type of scope. But there might be cases when you actually want to cancel an individual job. So we want to be able to say, OK, just cancel job 1. But this means that we only have one child. That child will tell the parent that it's canceled, but all the other children should be OK. And that's right. That's the behavior of coroutines. So a canceled child doesn't affect other children, other siblings. So how is this happening? What's the internal mechanism? So if we look at the cancellation method signature, we see that actually we have a cancellation exception there. So this cancellation exception is actually a special exception for coroutines, because it's their way to differentiate between cancel and the fact that an exception was thrown. So I said that the child tells the parent that, hey, I got canceled. Actually, there is an actual check whether, hey, is this a cancellation exception that just returns true, which means that, OK, the child's cancellation was handled, so it the parent knows that it doesn't need to do anything else. OK, now let's take an example and see what's the connection with the lifecycle and what happens there, actually. So in our example, we want to print a message twice a second, 5 times. So for this, we use the system current time in milliseconds, and then we just set the next print time to 500 milliseconds. And we're just printing hello 5 times. We're talking about coroutines here. So we're launching a coroutine. So we'll just let the coroutine run a little bit for 1,000 milliseconds, and then we'll call cancel. So when we're calling launch, the coroutine gets in the active state. We're delaying for 1,000 milliseconds, therefore the coroutine starts running, and then we start seeing stuff on the screen or on the terminal. But then we're calling cancel. We're printing the cancel. Our coroutine goes in the canceling state. We're printing done, because cancel is not a suspend, it doesn't block. But then we see that more hellos are printed, that actually our coroutine finished our work, although we said cancel. And only afterwards, after that work was finished, it gets in the cancel state. So the problem here is actually that the cancellation of coroutine code needs to be cooperative. So you need to make sure that the code you write is cooperative. So what does this mean? What do you need to do? So to implement cooperative cancellation, you can use something like job is active or ensure active or yield. So looking at our example, in that while specifically, we can add a check for is active. And this is the place where we say, OK, because we have a while and we do our work only in that while, we can say, OK, it's no longer active, so we'll stop. We're finishing the work. We can also use ensure active. Under the hood, ensure active actually does the same check for is active, but it also throws a cancellation exception. So this means that is active, the val is active, will allow us to do an action before finishing the coroutine, whereas ensure active will just instantaneously stop the work because it will just throw the cancellation exception. If you want to use a suspend function, you can use yield. Just that yield does a little bit more than that. So actually, yield is something that you should use when you're doing a CPU-heavy computation that may exhaust the thread pool. So yield also checks whether the coroutine job was completed. And if yes, it will throw the cancellation exception. So this means that if we put this yield method inside our while, we have our first hellos inactive, then cancel gets called, our coroutine gets in the canceling state. But then, because we have that yield, automatically we get to the canceled state, because yield will be the one that checks, hey, am I canceled? Yes. So it will just stop. The same kind of logic of printing something on the screen 5 times can be implemented like this. So here, we're just using a repeat and a delay of 500 milliseconds. Well, let's see what's going on here. So our coroutine is active. We're printing the hello, canceling, and canceled. So everything works well. Why? We didn't use is active or yield. So this is because of the delay. Because delay is using a suspend or creating a suspend cancelable coroutine. So this means that delay already has this mechanism of cancellation, of checking whether the coroutine is canceled or not, and it will cancel for us. Even more, all the suspending functions in the KotlinX coroutines are cancelable. But if you create your own suspending functions, make sure you're making them cancelable. So for example, let's say you're creating a launch and you have some work being done, and all of these work 1, work 2 are suspend functions. Then you can call yield or ensure active between them to check for that cancellation. And then in that, each individual suspend function, do that check again, just to make sure that your cancellation, your code is cooperative at cancellation. So let's take another example. Let's say that we have this kind of a listener. So this is actually the retrofit call that gives us a callback on response successful and on failure. If we want to convert this listener to coroutines, we would use a suspend coroutine. But this suspend coroutine isn't cancelable, isn't cooperative with cancellation. Rather, here, if you want to convert this into something that's cancelable, we need to use suspend cancelable coroutine. So this one provides us an invoke on cancellation, where we can call that retrofit call.cancel to ensure that the call that we're doing to the network is canceled. But when you're using suspend cancelable coroutine, you're not inside a job or a coroutineScope context. So this means that mechanisms that I told you before, like job is active, doesn't work. Similarly, you can't call suspend functions like yield because you're not in the right context. So let's say that we want to suspend until the job is completed. So for this, we know we could use join if we're using jobs, or we could use await for deferred. But how does these work? How do these work, actually? So we know that join actually will block the running. So this means that we're in the active state, and join will just make us block there until the entire coroutine job is finished. And only afterwards, we're getting in the completed state. And even if we're calling cancel, the coroutine has already canceled, so it doesn't have any effect. If we're reversing the order, so we're first calling cancel and then join, we see that we have first the first two hellos being printed, then our cancel gets called, we're getting in the canceling, then cancel state. So the role of the join is just to make sure that whatever work was happening there in the coroutine is finished. This, I think, is also specifically helpful if you're testing your code and you want to make sure that the coroutines that you're launching have finished. OK, how about await? So we would use await when we need the result from that coroutine. So this will do exactly the same behavior as join, as in it will wait for the entire work to be completed, it will get the result. And then once we call cancel, the coroutine was already completed, so there's nothing to do. But what if we reverse the roles? What if we call await after cancel? So in this case, we're printing the two hellos, nothing new here, we're calling cancel. Our coroutine goes in the canceling state, and then for await, we get a crash. We get job cancellation exception. But actually, this shouldn't surprise us. What we want to do with await is to get that result. What result are we expecting to get for something that was canceled? So just make sure that you're not calling await after cancel. So actually, if you look internally at what's going on with await, there is an actual check of is the coroutine already completed, and it should throw if it was completed exceptionally. So if it was already canceled or an exception was, well, if it was already canceled, it will just throw that exception. So TLDR, in the case of join, if you're calling cancel if you're calling cancel before join, there's no action. If you're calling cancel before await, keep in mind that await will throw if it was already completed. So how do we handle cancellation? What if we want to do some other work when our code was canceled? So I told you before that we could use something like isActive. So this means that at the end of our while, we can do a check for isActive, and we can do that cleanup that we need. And we see that we're calling cancel, cleanup, everything behaves right. But if we don't want to do this periodic check for isActive, we know that suspending cancel coroutines are also throwing cancellation exception. So this means that we can wrap our work inside the try catch for cancellation exception. And then finally, we can do that cleanup that we need to do. But I told you before that suspending functions are cancelable in coroutines. So this means that if we're calling delay, actually nothing happens. That cleanup done isn't called. So this is because a cancelable coroutine is not able to suspend. But if you do want to do some work that requires calling a suspend function, once the coroutine was canceled, you need to use with context of non-cancelable, and there put your logic. But again, with context is a suspend function. How does this work? Why does this work? So actually, with context is a bit special because the first thing it does is change the context, and only afterwards check whether is this in an active state or not. And if you would look at the implementation of non-cancelable, it says that it's always active. So this is what keeps us from canceling. And our coroutine will actually be in this in the canceling state as long as the work in the with context needs to be finished. And only afterwards it will go inside the cancel state. OK, so if you're using a suspend cancelable coroutine, then in the invoke on cancellation, this should be the place where you're doing whatever cleanup you need to do. So TLDR. Cancellation of coroutine code needs to be cooperative. So make sure that you change your code in such a way that you're implementing this cooperation. So I said before that we get into a canceling state because of two reasons, either cancellation or because of exception. We heard about cancellation. Let's hear about exceptions.
Thank you, Florina. So usually, cancellation is triggered by a user action, but now we're going to see the exceptions happen when a coroutine or a computation fails. So we're going to see how that affects the task hierarchy. So imagine that we are in this situation that we were before, but for some reason, the first computation that we are running fails. So how is that going to work? How is that going to happen and affect the hierarchy? The failure of a job is going to cancel the parent job and other siblings. So if we see this, we can say here that the child is going to notify its parent that it failed for some reason. And the parent, what it's going to do is say, OK, now I'm going to propagate cancellation down, so all the rest of the children are going to be canceled. It's going to cancel itself, and then it's going to propagate cancellation up to the parents. So if we take a look at the source code in the job support file, we'll see kind of the same method that we saw before. And this child canceled is going to be called in the parent job when a child failed because of a cause. And so here, the important bit is the Boolean return type, that this represents whether the exception has been handled or not. So we saw for cancellation, because just the normal coroutines machinery is always going to return true because it was expected. But if not, it's going to do something else. So if we step in the code, we will see what it does is first it's going to cancel the children, and then it's going to propagate the cancellation up, just as we saw. So that means that the cancellation is going to be propagated up until when? Well, it's going to affect the scope as well. And the scope here, because also it has a job, and if some of the children of the scope fails, what it's going to do is going to cancel the scope and the rest of the children. And you have to watch out for this, because a canceled scope cannot start more coroutines. And what that means is that again, the scope is going to destroy completely everything. But here, if a child fails and we don't control and we don't handle those exceptions, it's going to kill the whole thing. And so if we are in a UI-related scope, it might kill the whole UI component, and the user won't be able to interact with the screen anymore. And at some points, we don't want to have that behavior. So do we have any other alternative? An alternative here is a different implementation of job, which is the supervisor job. And this is just another job with certain characteristics. And for example, you can use it here. You can pass it to the coroutineScope as if it was another job. And the failure of cancellation of a child with a supervisor job, it is not going to affect the rest of the children. So here, imagine a child either fails or gets canceled for some reason. It is going to notify the parents, and the parent doesn't care. It's going to ignore it. So if we take a look at the source code, it's pretty interesting, because here we have the supervisor job implementation. And if we take a look at the child cancel method, which is the only one that it overrides, it always returns false. Means that it's not doing anything. But that also means that exceptions are always going to be propagated up if you don't catch them. So uncaught exceptions always propagated up. And that happens regardless of if you are using a job or a supervisor job. So you have to be very careful with this. So at this point, how do you know if you should use a supervisor job or a job? Well, you have to ask yourself, do you want to cancel the parent? Do you want to propagate that cancellation up and down in the hierarchy? If that's the case, then use job. and if not, use a supervisor job. By the way, the same happens with the coroutineScope builders, with coroutineScope and the supervisor scope. These, in a coroutine, are going to create a subscope having the job or a supervisor job as a parent accordingly. We'll see more of this in a second. Watch out, number 2. A supervisor job only works if it's the coroutine's direct parent. And it is very easy to make mistakes with this. So let's take a look at this sample. We are going to create a scope, a coroutineScope, and now we are going to call launch with supervisor job as a parent. So here we are in this coroutine, and we want to do some parallel computation, so we have 2 nested launches, child 1 and child 2, both of them with respective jobs. So now what happens if child 1 fails? So we could imagine that because a supervisor job is there at the parent, then child number 2 won't get affected. But the truth is that that's not the case, because the parent, the direct parent of the child number 1, is the job that was created out of that coroutine, out of the launch. So that means that because of how it works, the machinery that we all saw before, child number 1 will communicate that cancellation to the parent, and that will affect child number 2. The parent will get cancelled too, and then what roles play the supervisor job here? Nothing, it's just the parent of that job, because the supervisor job here is in the parent context. It's not the direct parent of this coroutine that we just created. So how can we solve this problem? So one thing, we can use the supervisor scope, as I said before, because now you can logically group coroutines that you want them to work together. And so now with these 2 children, and because we have the supervisor scope, grabbing them, if child 1 fails, the direct parent of it will be a supervisor job because of the supervisor scope. So here, child 2 will be okay, and it can continue running. And just for completeness, the parent of the supervisor job is indeed the job that gets created out of the launch. Just to see more samples, if you don't need those parallel computation to be nested, then another thing you can do is just have a shared job, for example, this supervisor job, that you can granularly control which jobs you want to be affecting each other. Here will be the parents, and if one fails, the other one won't get affected. The same, just if you install it in the coroutineScope, having their supervisor job there, and you create multiple coroutines without the scope, all of them will be kind of independent and won't affect each other. Another watch out, check the implementation of predefined scopes. So Florina showed before that we had in Android this view model scope or lifecycle scope, but if you're using any other external library, they could define their own scopes. Watch out for that and make sure, because the scopes and the jobs that the scope is configured with is going to affect the way cancellation and exceptions work. So in this case, if we take a look at the lifecycle scope, we can see that it's configured with a supervisor job and dispatchers.main. So by default, everything is going to run in dispatchers.main, and children won't get affecting each other. Cool. So now we said that exception and code exceptions are always going to be propagated up. So at some point, we will have to catch them. We will have to deal with them. And the good thing about coroutine is that you can use the built-in language support to deal with errors. So we have to define 2 categories here. The first category is the thrown exception. So as soon as an exception happens, that exception is going to be propagated automatically. And here we can think of the launch coroutine builder as an example. And the other category is exposed exceptions. So in this case, it is not until you call one function when you will get that exception. And this is the case of async. And async, until you don't call await, you are not going to get that exception. And just a caveat here, it works with root coroutine. So root coroutine is the direct child of a scope. For example, here we have a launch with an async nesting. If async fails, it is going to notify the parent because both are jobs. So it is it's going to notify the parent is launched, and launch is going to automatically propagate that exception. So here, not calling await is not going to make any difference. The exception is always propagated. So as I said, we can use the built-in language support. And for that, you can use the traditional try-catch approach. We're going to see how you can catch or how you can deal with those exceptions. So the first one here, we saw that launch is going to automatically propagate that exception. Therefore, you should grab those, that code that comes through exceptions inside the try-catch. And then that exception will be handled if it happens. Whereas with async, it doesn't work in that way. So you don't need to grab it inside the try-catch, because async itself, it is not going to throw the exception. Calling await will throw the exception thrown in async. And so having that in the try-catch then is going to work as expected. It's going to be handled. But if you noticed, we're using a supervisor scope. And this is because the supervisor scope, it is not going to notify the parents, but it's not going to handle the exception either. So it is up to the code, or to the coroutine, to handle that exception. If we change supervisor scope with a coroutine scope, here, on the other hand, it is going to automatically propagate the exception. Because everything is a job here, async will notify the parents, and coroutineScope will start notifying their parents. So that exception is not going to be caught, and that catch is not going to be called. So at this point, boom, you might not expect that, and your application might crash. And that's try-catch. There is another approach that you can take, which is run catching. And I don't know if you're aware of this, but this is just a method from the Kotlin standard library. And basically, you can grab any code that comes through exceptions inside run catching, and this will give you a result. And the result is going to be either a failure or a success. And here you can do your if-else, depending if it's success or not. And if we check the implementation, it just uses a try-catch under the hood. So again, this is just the regular way to handle exceptions. So use one or the other depending on your use case or the one you like more. So at this point, it's like, OK, I'm catching all my exceptions. I got this. Nothing else can go wrong. However, sometimes something unexpected can happen. And for that, we can use the coroutine exception handler that we mentioned at the beginning. The coroutine exception handler is an optional element in the coroutine context, and it's going to handle uncaught exceptions. So here we can define it, just a coroutine exception handler with a variable. You get the coroutine context on when the exception happened and the exception itself, and then you can do anything you want with that. It doesn't mean like you have to silently catch all the exceptions. We are not advocating in favor of that. Here is that, for example, if you want to notify your analytics team that an unexpected exception happened, you can do that, and then you can do whatever you want with it. But there are some caveats. When is it going to be called? And it's going to be with automatically propagated exceptions. That means that it's going to work with launch as a root coroutine, but not with async. And where? When it's going to be installed is the scope. Either it's installing the scope, the root coroutine, or a supervisor scope direct child. If we take a look at the implementation to understand this better, we will see that this method, when the coroutine is finishing, will be called. And if the parent is not handling the exception, for example, with a supervisor job, then it will be up to the job, to the coroutine, to handle that exception. You can see it with handle job exception. If we step in, we can see that the first thing it does is checking if there is a coroutine exception handler installed in the context. And if that's the case, then you call the handle exception method and then returns. It doesn't do anything. So that exception is caught and nothing else happens. But if that's not the case, then it will fall back to the global handler. And if we step in here, you will see that you can install additional extension handlers, and it will end up calling this the threads uncaught exception handler. That in the JVM, it might lock the exception to console, but in Android, for example, it will make your application crash, regardless of the dispatchers that you use. And why do we have this use additional extension handlers? Why you can do that? You can do it using the service loader. And a good use case that I found is for testing. Like if you want to test that the thread's default uncaught exception handler is going to be called, you can do that in testing by installing your own coroutine exception handler with the service loader. Cool. Enough theory. Just show me how I can use the coroutine exception handler. So here we can define the variable, as we were doing before, and now we just want to print to console. So now we can create our own scope, and then we can create coroutineScope, and then we pass in the handler as the coroutine context as a parameter. And now, if at some point in this scope a launch happens to throw an exception, for example, here we have inner launches, that exception is going to be caught by our handler. Same way, if we put it in the root coroutine, in the outer launch, it is going to be handled the same way. However, if we pass it into the inner launch, yeah, you will see fireworks. And this is because the inner launch, as we saw before, is going to notify the parents. The outer launch doesn't know anything about the handler, so it is going to propagate the exception up. Another example here, you said you can use it as a direct child of Supervisor Scope. And here you install the handler in there. It is going to be OK. You are going to catch that exception. However, if you use the coroutineScope, you know what's going to happen. So these are the different ways you can handle exceptions with coroutines. And TLDR here, use Supervisor Job to avoid propagating the cancellation up and down. When it makes sense, of course, for the use case, and not use the job otherwise. You know now that uncaught exceptions are always going to be propagated, so catch them all to not see fireworks. And this is the end of the presentation. Hope now that everything you learned today, you can apply that to your application. And so you are not going to, having a weird behavior when dealing with cancellation and exception. So we hope that nothing catches you unprepared now. Thank you so much.
Thank you.